Sampling. Sampling is the action or process of taking samples of something for analysis, and it's also the technique of digitally encoding music or sound and reusing it as part of a composition or recording. The definition of population mean and sample mean are as follows. A population is a collection of persons, objects, or items of interest, while a sample is a portion of the whole and if properly taken is a percentage of the whole. A population mean is represented by the Greek letter M, while the sample mean is represented by the X bar. Please notice the formula given on your left side. The following video is a computation on how to get the population mean and sample mean.
The population mean, or mu, is called a parameter. It's an identity of what you're looking at. You can look at it as the gold standard. That's what you're comparing all the statistics you're coming up with when you're approximating. And so X bar, or the sample mean, is a statistic. It's an approximation in that you're looking to get what the parameter is with limited data. And so that's the difference between the two. You're looking at the mu is a parameter, it's what the population is. X bar tries to get you what the population is with the limited information it has. And the reason for that is, very rarely do you have the capability of doing a census where you can look at everything. Usually it takes up too much time, too much resources, so we use samples, and with those samples we come up with statistics that then approximate what the parameter is. For visualization, I'm going to be using a fairly simple population. It's only going to be a population of 10 people of differing heights, and so here's the numbers of the heights. So how do you go about calculating that? The calculation for mu is the summation of each x divided by capital N. So capital N in this case is 10, and then for the summation we have 60 plus 71 plus 76 plus 56 plus 52 plus 65 plus 49 plus 53 plus 67 plus 64, which gets you 613 over 10, which equals 61.3. So now we know the parameter mu is 61.3 inches. When it comes to looking at samples, I thought it'd be nice to look at two different types of samples just to show you a kind of trend that tends to happen as you increase the sample size. So the first one is using a sample of 3, the second one is using a sample of 6. When you calculate X bar, you calculate the summation of each x just like before with mu, except you're dividing by small n. So you're not dividing by the population, you're dividing by the sample size. And so we have 71 plus 56 plus 64 over 3, which gives you 191 over 3, which gives you 63.67. And this is rounded. And so it's close to what the mu is, but I'm sure if we increase the sample size, it'll get closer. And so that's exactly what we'll do, is we'll increase the sample size. So we have X bar equals the summation of Xi over N, and N in this case is 6. From that 6, 76 plus 65 plus 53 plus 56 plus 60 plus 52 to give you 362 over 6, or 60.33 rounded. So in this case, even though it's below what the parameter is, it's closer to the approximation of it. And that's typically what happens when you increase the sample size. The basic takeaway of this is, as you increase the sample size, X bar, the statistic, gets closer to mu, the parameter, in approximation. You'd very rarely ever have a population of 10 and then want a sample of it, because in most cases you would just take the 10. In most cases you'll have something where you have 1,000 people in a city, so you take a sample of 100 people, and then you approximate the parameter, mu, with the X bar of the 100 people. So that's where you get the statistic from, and as you increase it, if you go from 100 to 400, your statistic is going to be more approximate to what the parameter is.
When is the sampling error occur? Sampling error is a statistical error that occurs when an analyst does not select a sample that represents the entire population of data. For example, results found in the sample thus do not represent the results that could be obtained from the entire population. There are 5 types of sampling error. These are population specification error, sample frame error, selection error, non-response, sampling errors. Population specification error. This error occurs when the researcher does not understand who they should survey. For example, imagine a survey about breakfast cereal consumption. Who to survey? It might be the entire family, the mother, or the children. The mother might make the purchase decision, but the children influence her choice. Sample frame error. A frame error occurs when the wrong subpopulation is used to select a sample. Way back in 1936, the sample frame was from car registrations and telephone directories. In 1936, many Americans did not own cars or telephones, and those who did were largely Republicans. The result wrongly predicted a Republican victory. Selection error. This error occurs when respondents self-select their participation in the study, only those that are interested respond. Selection error can be controlled by going extra lengths to get participation. Typical survey process includes initiating pre-survey contact requesting cooperation, actual surveying, and post-survey follow-up. If a response is not received, a second survey request follows, and perhaps interviews using alternate modes such as telephone or person-to-person. The non-response errors occur when respondents are different than those who do not respond. This may occur because either the potential respondent was not contacted or they refused to respond. The extent of this non-response error can be checked through follow-up surveys using alternate modes. The last error is sampling error. These errors occur because aberration in the number of representatives of the sample that responds. Sampling errors can be controlled by careful sample design, large samples, and multiple contacts to assure representative response. The behavior of the sample mean against the population. There is arguably no more important lesson to be learned in statistics than how sample means behave. It explains why statistical methods work. The vast majority of the things people do with the statistics is compare populations, and most of the time populations are compared by comparing their means. The way individual observations behave depends on the populations from which they are drawn. If we draw a sample of individuals from normally distributed population, the sample will follow normal distribution. If we draw a sample of individuals from population with a skew distribution, the sample values will display the same skewness. Whatever the population looks like normal, skewed by model, whatever a sample of individual values will display the same characteristics. This should be no surprise. Something would be very wrong if a sample of individual observations didn't share the characteristics of the parent population. We are now going to see a truly wondrous result. Statisticians refer to it as the central limit theorem. It says that if we draw a large enough sample, the way the sample mean varies around the population mean can describe a normal distribution. As you can see in the illustration given, the parent population is the top panel shows population skewed to the right, while in the middle panel shows a sample of 25 observations drawn from that population. The distribution of means is on the bottom panel shows the sample mean. And one more time, in each case, the individual observations are spread out in a manner reminiscent of the population distribution. Sample means, however, are tightly grouped. This is not unexpected. In each sample, we get observations from throughout the distribution. The larger values keep the mean from being very small, while the smaller values keep the mean from being very large. There are so many observations, from large to small, that the mean ends up being average. If the sample contains only a few observations, the sample mean might jump around considerably from sample to sample, but with lots of observations, the sample mean doesn't get a chance to change very much. Here's how those means from the 10,000 samples of 25 observations each behave. They behave like things drawn from a normal distribution centered about the mean of the original population. At this point, the most common question is, what's with the 10,000 means? And it's a good question. Once it's sorted out, everything will fall into place. So that's all, folks. Thank you and stay safe.